Hi, everyone. We'll just give it a minute to let people continue to join and then we'll get started. Hello, everyone. Thank you so much for being here. On behalf of the Environmental Finance Center Network, welcome to today's webinar on wastewater treatment process control concepts and calculations. My name is Owen Volk from the Syracuse University Environmental Finance Center. Before we begin, we're going to go over a few logistics and then we can get started. During the webinar today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it in the GoToWebinar question dialog box at any time throughout the session. We will be saving your questions for a facilitated Q&A session at the end of the presentation. After the webinar, you will receive a follow-up email that includes a link to the recording and any other information you may need. You can also download the slides from today in the Handouts tab in your GoToWebinar control panel. This webinar has not been submitted for pre-approval of continuing education credits, but eligible attendees will receive your certificate of attendance for their personal record. To receive a certificate for this session, you must attend for the entire session and register and attend individually using your real name and unique email address. Certificates will be sent via email within 30 days of the webinar date. If you have questions or need assistance, please contact smallsystems@syr.edu. Now, for a little bit about us. The Environmental Finance Center Network provides training and technical assistance to small water and wastewater systems in all U.S. states and territories through our building technical, managerial, and finance capacity programs. If your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through our request form, which I will be sharing shortly in the chat. One of the many ways EFCN can support your community or utility is through our free funding application support. Struggling with an infrastructure funding application? Falling short on project funding? Not sure where to start? EFCN is here to help. Submit a request through the link in the chat to receive tailored support based on your project needs. And on that note, we can get started. I would like to introduce our presenter for today, Greg Pearson, Water and Wastewater Trainer at the Great Lakes Environmental Infrastructure Center. Welcome, Greg, and I will hand it over to you.
Thank you, Owen, and welcome everyone. I'm glad you're here. I'm going to share my screen here. Can you see the presentation yet, Owen?
We have the slides, but it's not in presenter mode. Now we're good.
Okay, thank you very much. I'm going to go off camera, everyone, as so that the camera doesn't interfere with anything. And I want to welcome you to today's class. We're going to be looking at different forms of wastewater treatment process control today. So it's going to be kind of a wide-ranging topic today. And you know, we're in a nationwide project, EPA-funded project with the Environmental Finance Center. And Owen and I were just looking at the map. And Owen is at Syracuse University in New York, and Owen says he's about at the top right portion of that little Y in the New York symbol. And I'm presenting to you from the Great Lakes Environmental Finance Center, which is at the top of the upper peninsula of Michigan, that little jagged point above Wisconsin there. And so we're serving Region 5, and we are working with quite a few systems, helping systems develop asset management plans, put in funding applications, develop rates, things of that nature. So there's a lot of technical assistance going on, and so that's our mission, to serve small water and wastewater communities, help them to build capacity, financial, technical, and managerial capacity. And our center is located at Michigan Technological University, and my name is Greg Pearson. They call me the Water and Wastewater Systems Trainer, also part of the TA team, the Technical Assistance team. And you can definitely, by the end of this webinar, it's okay if you want to ask for additional material or you want to follow up on some questions. I'll leave my email with you at the end. Now, today we're going to be covering some different aspects of secondary wastewater treatment. We'll start out by looking at some general principles and delve into biochemical oxygen demand. That's going to be a constant that's similar across the different types. Then we're going to look at activated sludge process control, which is going to cover the food to microorganism ratio and the mean cell residence time calculation. We'll even delve into a little bit of lagoon process control. And then we're going to segue into some trickling filter, which this is not a suspended process. This is a fixed media process. And we're going to look at organic loading and hydraulic loading. So we're going to look at some different aspects of secondary wastewater treatment. And I'm hoping that we can draw some big picture conclusions. I hope you enjoy the training. We'll go to our first poll now. And this poll asks, which of the following statement best defines the term secondary wastewater treatment? And Owen's going to bring up that poll. And I can't actually see the polls, Owen, so you feel free to let me know when people have responded and if you could, what the answers are.
Yeah, absolutely. Give it about a minute, and then we'll get those results to you.
Thank you for participating, everyone, too. You guys are always such a great audience to work with. And I know we're kind of separated by this Zoom platform, which makes it difficult for us to talk with each other, but feel free to use the chat and submit questions as we are going through.
Okay, we're going to give it another 10 seconds. Okay, so for the poll results, 71% said a process that uses microorganisms to consume organic wastes. 16% said the second step of any wastewater treatment process. 3% said a side effect of treatment that removes ammonia. And 10% said a process that uses coagulation and filtration.
Okay, very good. Now, if we look up the actual definition of secondary wastewater treatment, that's a term that's used to define any process that uses naturally occurring microorganisms to consume waste. Now, is a little bit of a trick question because it's also called secondary because it follows primary treatment. Primary treatment is settling of settleable solids before the wastewater enters the actual secondary treatment process. The main focus of secondary treatment is to remove BOD. BOD means waste that causes oxygen demand. And this, I drew this triangle around the organic waste, dissolved oxygen, and bacteria because it's almost like the fire triangle. For a treatment to take place, we need to keep bacteria, dissolved oxygen, and the organic waste all in contact for a long enough time so that bacteria can consume the waste and remove it from the water. And in essence, it becomes the cellular mass of bacteria and other microorganisms. By the way, the coagulation and filtration could be added on to the end of a wastewater treatment process, and that would be called tertiary treatment. And a lot of the reasons why we're doing secondary treatment is because if the waste were to get into receiving water, it would continue to cause oxygen depletion because bacteria would be consuming waste in the receiving water, and it would negatively affect the life forms in that receiving water. It would they wouldn't have sufficient oxygen to breathe, so they'd either move out or die. Some other things are nutrients, nitrogen and phosphorus, that can lead to algal blooms, and when the algae dies off, that also adds to oxygen depletion. Decomposing matter as a result of all these processes can continue to release BOD and nutrients. And finally, TSS, total suspended solids, can interfere with aquatic life. It can do things like clogging the gills of fish, and also can promote excess plant growth and block light. So there's lots of, these are kind of like the main things that are regulated in an NPDES discharge from it. BOD, nutrients, and TSS, and of course ammonia as well, which would be toxic. Now, so this biochemical oxygen demand concept is going to be central to all of the process control equations that we'll look at. So let's delve into biochemical oxygen demand for just a little bit here, and we'll define what it is, how it's measured, and we'll end up with a way to calculate the pounds of BOD per day using the pounds formula. So let's look at these couple slides before we delve into activated sludge. So the BOD is a way to measure the strength of a waste stream. It directly measures the oxygen demand, and it kind of indirectly measures the actual amount of waste that is in a waste stream. So you have microorganisms. When they consume BOD, they require oxygen to do so. And BOD is measured in a 5-day test that measures how much oxygen the organisms are requiring to consume that waste in the sample bottle. So let's look at kind of a concept of how that works. So you would take a sample bottle, and these BOD sample bottles are 300 milliliters, and you would take a portion of the sample. For example, if we had a 10 milliliter sample of wastewater, and the rest was makeup water, that would be a 0.033, or 1/30th of the bottle would be our sample, and the rest would be makeup water. And we would conduct the test. What is the oxygen level at the beginning of the test, and what's the oxygen level at the end of the 5-day test? And we subtract, and we could see, in this case, we measured 9.85 milligrams per liter of DO at the beginning and 3.42 at the end. We subtract, and we see that we used 6.43 milligrams per liter of oxygen. Now remember, that was only 10 milliliters of sample. That was only 1/30th of the test bottle. So we'd have to multiply that by 30 basically, or divide by our p-value, they call it. This p-value was the proportion of the sample to the sample bottle. So 10 divided by 300 gives you this 0.033. So we divide that 6.43, that's our oxygen that was used, by this 0.033, which is the same as multiplying by 30 to get the overall concentration for a whole liter of water. So you see, we have 194.8 milligrams per liter of BOD, and this is foundational to all the process control calculations that you might want to do in any kind of a wastewater treatment, or to measure the effectiveness of your treatment plant. Does everyone follow that? Is anybody confused on how BOD is determined here? Give me some feedback if you have a thumbs up where you're good. Are you seeing any feedback, Owen?
I haven't gotten anything through chat yet. Seems like everyone is set.
Okay.
Yeah, it's looking good.
Good. Thank you for giving the feedback, everyone. Now, we're going to segue into figuring out how many pounds per day of BOD. We've already figured out how do we determine the concentration of BOD. From that previous example, we determined a BOD concentration of 194.8 milligrams per liter. We'll use that concentration in this example. So we have a plant that has an inflow of 2 mgd, 2 million gallons per day coming in, and the concentration of the BOD is 194.8 milligrams per liter, and we're asking how many pounds per day. So what we're going to do is we're going to use this pounds formula, and the pounds formula is the flow in mgd the concentration in milligrams per liter, and the weight of water, 8.34 pounds per gallon. Now, I'm going to show you how we can just plug the numbers in and use this. Then I'm going to show you a little bit about the pounds formula after this, how it might work. So if we just plug in the known data, 2 mgd times 194.8 milligrams per liter times 8.34 pounds per gallon, that'll give us the pounds per day of BOD. Did anyone calculate that answer for us? If you have the answer, put it in the chat and we'll compare. I might have got something wrong, so you have to watch me. You have to get your
Well,
calculators out and do it.
while they're doing that, someone did have a question. Well, there's two questions that came through. One was about the test bottle. What is it made of? And then also, how do you calculate the p-value?
Yeah, the p-value is your sample size divided by the volume of the test bottle. So your sample size in that case, in that example, was 10 milliliters, and the bottle is going to contain 300 milliliters of liquid. So 10 divided by 300. The other portion of the water, um, the other 290 milliliters is probably like deionized water. Now, what the bottles are made of, I assume they're glass or Pyrex, but that's probably something that we'd have to ask a lab person. I'm not actually a lab person. I wish I knew a little bit more detail about it. But let me know if that was what you're getting at. But if you send me an email, I do have some additional information uh, that I could send you.
Okay, and we have tons of responses, some more precise than others. 3,249.26 is the most precise that we have.
Okay. And I rounded the 0.26 up to 0.3, so 3,249.3 pounds per day. Very good. Excellent job,
Also, we
everyone.
got responses from people that work in labs. It's made of glass, and they have
Oh,
plastic versions.
oh, okay. Thank you very much. I'm so happy that we have some professional lab people on the line. Thank you so much for doing that. Um, Now, understanding the pounds formula. If you're a dimensional analysis person, the pounds formula might drive you crazy because you have million gallons per day, and then you have some metric units, milligrams per liter, and then you have the weight of water, and you're wondering what in the world is going on with this pounds formula. Well, you could just use it, but you can also have a better understanding of it. And I'm going to show you a couple of different ways to think about it. If I rewrite this equation, and instead of MGD, I write 2 million gallons per day, and I rewrite the milligrams per liter as parts per million, and I put 194.8 parts per 1 million parts, and then times the weight of water, I get the same answer. I want to show you something additional. If we look at the weight of 2 million gallons of water, we just take that 2 million gallons times 8.34 pounds per gallon. So we're talking about 2 mgd, 2 million gallons of water actually weighs 16,680,000 pounds. Now, the weight of the BOD is 194.8 millionths of the water weight. So if I take that water weight, 16,680,000 pounds, and divide it by 194.8 millionths, in other words, I times it by 194.8 and then divide it by 1 million, I also get the same answer. So we're assuming basically that the weight of the constituent, in this case, BOD, it's a portion of the water weight. So that's how the equation is somewhat working. I hope that gives you a little bit additional insight into how the pounds formula works. If that was helpful, let me know. If that just confuses you more than you needed to be confused, you can let me know that as well.
I have one person wondering, is the 8.34 pounds per gallon a constant?
Yes, 8.34 pounds per gallon is it's the water weight, and I think it defines it as the weight of pure water at sea level, I think. Um, so, as you go farther away from the earth, the weight is going to change a little bit. As you have dissolved substances into the water, like ocean water is a different weight than pure water. And So there's some slight variations. If you're a chemist or a physicist and you're trying to have very, very precise measurements, the 8.34 might not work as well. But if you're just trying to uh, design a water system, 8.34 might work good enough uh, for uh, for those purposes. So it's a matter of the precision is a matter of what you're using it for. But for the water and wastewater uh, topics, I think 8.34 is good, and we consider it to be a constant, yes. So let's delve into some activated sludge processes. We're going to look at two process control equations. One is the FM ratio, and we're looking at the ratio of BOD coming in, which is the food that we're going to feed to our microorganisms, and the microorganisms is the pounds of mixed liquor volatile suspended solids, or the amount of the pounds of microorganisms in the aeration tank. And we want that ratio to be fairly constant or within a certain range. So we're looking at, do we have the right balance? If we don't have enough food, our microorganisms are going to suffer. If we have too much food, or we're not going to have complete treatment um, by the time we get to the end of the tank. The MCRT results in a number of days that solids are remaining in the system. So you have the total pounds of mixed liquor suspended solids in the system, and then we divide that by the pounds per day of solids that are leaving the system. So we're going to define and explain those a little bit more, but we're looking at what's the average time that the solids remain, because the solids are recirculated in the activated sludge process, and we're going to delve into that a little bit more. If we look at the overall layout of a basic activated sludge plant, we have preliminary treatment, which would be screening and grit removal, but then we get to this primary treatment. The primary clarifier allows settleable solids to be removed, and then only after that, after the settleable solids are removed, do we get to the activated sludge process, which is the aeration tank and the secondary clarifier. The aeration tank is where we mix the incoming influent with return activated sludge, heavy with microorganisms. They consume the waste, and then they create a biomass which is settled in the secondary clarifier. So the secondary clarifier is a lot of microorganisms being collected there and recirculated back to the aeration tank. We have two flows, the return activated sludge and then the waste activated sludge. And remember, though, we're taking the effluent from the primary clarifier. So this consists, the solids in that flow are not settleable. They're suspended solids. They wouldn't settle out easily. So we have to do something to cause um, those solids to be able to settle and also to be able to remove the BOD. So if we focus in on just the activated sludge portion here, there's our aeration tank. We have the primary effluent coming in, and the settled sludge, which is heavy with activated sludge microorganisms, is mixed with that influent into the aeration tank. So you have food and bugs coming into the beginning of that aeration tank. By the time we get to the end of the aeration tank, we hope that the food is gone, the BOD is gone, and we have just cellular biomass that settles in the secondary clarifier. This mixture between the return activated sludge and the incoming BOD is called a mixed liquor. So you can think of it as like a dining hall where we're feeding our microorganisms. And so we have this incoming waste and the return activated sludge coming together, creates the mixed liquor. I have an actual image of this happening here. You can see in this aeration tank, we have we call it the primary effluent. It's the influent also to the aeration basin. That's the untreated wastewater. And then we have that return activated sludge. You see it's dark and thick with microorganisms that are hungry to consume the waste. At the beginning of the tank, we have a lot of BOD, but there's also lots of bugs, and the bugs consume that BOD and convert it into cellular mass. They reproduce, they grow. At the end of the aeration tank, it dumps into that secondary clarifier. This is where we collect the microorganisms or the settled sludge, activated sludge. And if we kind of look at a diagram of the secondary clarifier here, at the end of the aeration tank, it's mixing. It's being aerated and mixing, and so that discharges into the secondary clarifier and settles. And you got a bunch of hungry bugs that are settled. You got the return activated sludge that you can adjust higher or lower. You got the waste activated sludge that you can adjust higher or lower. So according to our process control calculations, we can adjust these sludge flows. Do we want more return activated sludge so there's more microorganisms according to the amount of BOD? Do we want to waste more sludge so that we lower the amount of bugs that are retained in the system or monosolids? The waste activated sludge determines how many solids are in the system and how long they're in the system. And remember, the final effluent, the water, keeps on going. The solids remain in the system longer than the water. The clarified water goes out to disinfection, dechlorination probably, and then discharge into the receiving waters. And here's kind of how the process might look. You got the plant flow that's coming in. You have aeration and mixing in this aeration tank. And here's your return activated sludge coming in with the plant flow, and then your waste activated sludge. For conventional sludge facilities, you might be the flow might be spending 2 to 5 hours in the aeration tank or something like that. But remember, the solids are going to remain in the system a lot longer, somewhere between 3 and 15 days, depending.
So we did have a couple questions come in.
Yeah.
I don't know if you want to, it might just be easier to plug them as we go. So one of the questions was how much of the RAS needs to be returned? And then the other asks, does the RAS and WAS automatically settle to the bottom? Are there any agents that are used to force settling?
Well, let me see if I can go. Let's just go back to here as we talk about this. The recirculation rate is generally between about 20 and 50% of the plant flow. And often they'll set it in to kind of like pace with the incoming flow, 20 to 50%. There is an equation. I did not include that equation in this presentation. There is an equation to determine the plant flow. And so it gives you a starting point. Now, the actual FM ratio that you're trying to achieve, or the MCRT, is going to depend on some other things. One of the things that's going to depend on is how well the sludge is settling. And that goes to your second point. If we don't have good settling, it might be because we don't have the right FM ratio. I'm going to show you a slide in a few minutes that shows how settling, proper settling depends on the FM ratio. I'll show you that. Also, you could get something like filamentous bacteria it kind of keeps the sludge from being able to settle well. In that case, it's not really a normal practice to add something like coagulants or polymers to get the sludge to settle better. It's sometimes if you get a lot of filamentous bacteria, plants may actually have to do something like chlorinate to try to kill off the filamentous bacteria. But most of the time, we can just make some small adjustments to our FM ratio or our MCRT to tune in the settling. I hope that answers the question sufficiently. I think that's about as much as I can say about it right now. But I can provide you more information, more documentation on some source materials. I'd be happy to send you if you send me an email to gpearson@mtu.edu.
One final thing as we continue
Yes.
forward. Just to clarify, someone needed clarification on the acronyms of FM and MCRT.
Oh, FM is food to microorganism ratio, and MCRT is the mean cell residence time, or it means the average time that solids remain in the system.
Fantastic.
Right. Now, we often use these FM ratios as kind of a target range, and you might even want to refine it more. But in general, for conventional activated sludge, we're looking at a FM ratio of around 0.25 to as high as 0.45, and that somewhere in that range. If you're below that range or above that range, it might signal that you need to adjust. And the conventional, it's higher loading. You're having more food and more air. So 0.25 means you got one hamburger for 4 eaters, and 0.45 it's almost like 2 hamburgers for 4 eaters, something like that. Extended aeration plants like an oxidation ditch may have a lower FM ratio, a lot less food, more time, more solids. So they're operating between 0.05 to 0.15. Less food, more microorganisms, longer time. Now, food to microorganism, it's the ratio of the BOD coming in to the mixed liquor volatile suspended solids, which is microorganisms that are in the aeration tank. So you have the pounds per day of BOD coming in, that's your food. The pounds of MLVSS in the aeration tank is your microorganisms. Now we're gonna look at what MLVSS is too and how it's calculated. But overall, the food to microorganism ratio, you're going to do 2 pounds formulas basically to determine this. The incoming BOD, and we calculated this, the top part of this equation, the flow in mgd times the concentration of BOD in milligrams per liter times 8.34 pounds per gallon, and then the mixed liquor volatile suspended solids in the aeration tank. You're going to need to know what's the volume of the aeration tank in million gallons times the concentration of the MLVSS times 8.34. So you'll do the top pounds formula, the bottom pounds formula, and then divide to get that FM ratio. Okay? And now we're going to go ahead and go to poll 2 here. And poll 2 asks, which of the following would help ensure that there's sufficient biomass or microorganisms if the BOD increases? Depending on your knowledge so far of the FM ratio, you see a BOD increase, how are you going to make sure that there's enough microorganisms using your FM ratio?
Okay, so the poll is running. We'll give it another 30 seconds.
And thank you everyone for continuing to ask questions. It's not a problem at all. This webinar is for you. So, and thank you, Owen, for bringing those up when they come up.
Of course. We're going to give it another 10 seconds. And just to let everyone know, some of the math related ones I'll include while we work our way through, and then some of the other ones I'll save for the end. So we'll have you'll get your questions answered, don't worry. We can end the poll there. I will share the results. Okay, so it is pretty one-sided on this. 83% said use target FM ratio to determine required MLVSS and then adjust. 3% said do nothing. MLVSS will naturally increase in relation to BOD. 6% said increase the WAS flow to maximum as a precaution, and then 8% said do all of the above.
Well, the way that you can use the FM ratio is to look at your target ratio and to get an idea of how many pounds of bugs we should be including in the aeration tank. So or plant's running fine, let's say, at a certain BOD. Let's say you're in a tourist town and there's no tourist in the winter. You have a certain level of food coming in, and your microorganisms are just the right amount for that food. But all of a sudden, tourist season hits and your town doubles in population. And now you have this massive amount of BOD coming in, but not enough microorganisms in the aeration tank. So how are you going to know how much you should be shooting for? Well, the FM
Can I?
ratio would be a
Can
good
you
place
share?
to start.
Just reshare your screen again. We're not be able to see the slides.
Really?
Yes, it is kicked straight to your camera.
Oh, let me shut that off. Okay, let me see here. Is there something, can you send me a share screen link?
Yes, give me 1 second. I will take it right back, and then
How about now?
yes, now we're good.
Okay, I wonder if I accidentally clicked something and did that. Sorry about that, everyone. So in that case, we could use the FM target ratio, and I'll give you an idea how you could use this. You can say that the microorganisms, you could determine that weight by taking the food divided by the target ratio. And here's an example. Um, we have 500 pounds per day of BOD coming into the system, and the target ratio, let's say right in the middle of that range, about 0.35. In other words, we should have about 3 times the amount of microorganisms to the amount of food. So we could use this equation. We could say the 500 pounds of food divided by the 0.35 target ratio, and we'd see we need about 1,500 pounds, 1,429 pounds of mixed liquor volatile suspended solids under aeration. So that's how we could use it. And if we didn't have enough, we might be able to decrease the wasting rate and maybe increase the return activated sludge rate a little bit and allow the system to kind of balance before we make any additional adjustments. Now, how do we obtain this data for the mixed liquor suspended solids and the mixed liquor volatile suspended solids? Well, the MLSS, the mixed liquor suspended solids, that represents the total suspended solids in the aeration tank, and we use that in the mean cell residence time equation. Now, for the FM ratio, which we're doing now, we use the mixed liquor volatile suspended solids. That's the portion of the total mixed liquor suspended solids. Typically, it's around 70% of the total solids, and we use it as a way to measure the microorganisms that are available. Now, let's see how we do that. First of all, we take a sample and we filter it using a 0.45 micron filter. That captures the suspended solids that are in the sample. Now, just if you think about filtering an entire liter of water, we wouldn't filter an entire liter, we'd take a smaller amount. But if you filter out an entire liter of water and you weighed what the weight of the solids is, you'd weigh them in milligrams, and we're going to come out with a concentration as milligrams per liter. So that gives you also some insight in why that term is in the pounds formula, because we're using those terms to actually see what's the content of our mixed liquor suspended solids. So we filter the sample, we dry the solids we filtered out and weigh them. And then we can calculate the mixed liquor suspended solids concentration. Now here's an example. We take a 25 milliliter sample from the aeration tank. Now the aeration tank is churning and everything is mixed. You grab a sample and we use 25 milliliters of that sample and filter it and dry the solids. And we weigh them. When we find out that from this 25 milliliter sample, the solids that we filtered out, when they're dried, they weigh 75 milligrams. Okay, now we can put this into our little equation here to calculate the concentration of MLSS. We take the dry weight, which is 75 milligrams, and the sample volume, which is 25 milliliters, and we're going to end up converting that to liters by timesing it by 1,000. So we have a proportion there, and we transpose it to liters. So if we put our numbers that we just got into that equation, the dry weight of 75 milligrams divided by the sample volume of 25 milliliters, that's 3, right? 75 divided by 25 is 3 milligrams per milliliter. Times it by 1,000. 3 times 1,000 is 3,000. So we get 3,000 milligrams per liter uh, as a concentration of mixed liquor suspended solids. Now, remember, the mixed liquor volatile suspended solids are probably going to be about 70% of that. So let's look at carrying on this a little farther. Now, the first two steps are the same. We filter through a 0.54 micron filter. We dry the solids and weigh them. Now we have our sample of MLSS solids, but we're going to take an additional step in step 3. We're going to place those solids in a oven at 550 degrees Celsius. And what's going to happen is the volatile solids, the organic portion, are going to burn off. And then what we're going to have left is just the ash. The ash are the non-volatile solids, the non-organic solids that can't be consumed with bacteria. So if we look at the weight, the total weight of the MLSS in this example, we weighed 75 milligrams, and we subtract the weight of the ash, that'll give us the weight of the volatile solids. So in this example, I'm going to carry on with the same numbers that we just did for the MLSS, 75 milligrams, and I'm going to say the weight of the ash was 22.5. So we subtract that off, and we see the weight of the volatile solids, in this case, with this example, 52.5 milligrams per liter. And we can do the same process here of converting that to a concentration in milligrams per liter. You see we have the weight of the volatile solids in milligrams and the sample volume divided by the sample volume, and we convert it to liters. So in this example, we had 52.5 milligrams of volatile solids. We divide it by our sample size of 25 milliliters, convert it to liters, and we get that concentration for volatile solids. Does that make sense to everyone? Give me a thumbs up, or you can give a thumbs down if I lost you on some step there. Now,
People are putting into the chat. Everything's looking good.
okay, thank you so much for it. So I went through that is because that data is essential to use in our equations. So first of all, the FM ratio, we have an example here. We have a plant flow of 3 mgd, a BOD concentration of 275 milligrams per liter, and the MLVSS concentration is 2200 milligrams per liter, and the aeration basin volume is 1 mg. So now we know to calculate this, we're basically going to have 2 pounds formulas. The food at the top, plant flow times the BOD times 8.34. On the bottom for our microorganisms, our tank volume of 1 mg times the concentration of MLVSS 2200 times 8.34. When we plug our numbers in, there's our food. That's our BOD coming in, 3 mgd times 275 milligrams per liter BOD times 8.34. And there's our microorganisms, 1 mg times 2200 milligrams per liter times 8.34 pounds per gallon. Now, some of you that are attentive and you're a dimensional analysis oriented people, you'll notice that we have million gallons per day on the top and million gallons on the bottom. So with this FM ratio, it technically has the term of day on the bottom. We mostly use it in a way where it's kind of dimensionless. We use it as kind of a dimensionless ratio. But technically, you see, if you were paying attention to that, some people will actually write the FM ratio like 0.35 per day, something like that. So if we simplify the top and the bottom, the top I got 6,880.5 pounds per day. And on the bottom, I got 18,348 pounds of MLBSS. And when I divide the top by the bottom, I got 0.375. And that's right in the middle between that 0.2 to 0.45 range. So we're looking pretty good on the FM ratio. There might be reason to still to adjust it up or down for your particular plant. Now let's delve into the mean cell residence time, the MCRT. That's the average length of time in days that the solids remain in the system. And here's the equation. We look at the pounds of mixed liquor suspended solids. We're not dealing with mixed liquor volatile suspended solids now. We're looking at the total solids divided by the pounds per day of mixed liquor suspended solids that are leaving the system. And sometimes we can look at just the solids in the aeration tank and the solids leaving as waste activated sludge. Other times it might make sense to also include the volume of the solids in the secondary clarifier and also calculate solids that are leaving in the effluent. I'll show you an example of both of those. Now here's a very simple one here. What is the MCRT in days for a treatment facility with the following parameters? And we have the aeration tank is 2 million gallons, and the mixed liquor suspended solids is 2,400 milligrams per liter. So that gives us the solids under aeration. Then we have this waste activated sludge flow. The waste flow from the secondary clarifier, it's 0.15 mgd, and there's a concentration of 6,400 milligrams per liter. So that's leaving. Now you notice we can put these numbers into our equation here, pounds under aeration and pounds per day wasted. We're going to have 2 pounds formulas here. For the pounds under aeration, we have the aerator volume, aeration tank volume, 2 mgd times the MLS concentration, 2,400 milligrams per liter times 8.34, and we get 40,032 pounds that are under aeration. If we do the bottom part, the pounds per day that are wasted, we have our activated sludge waste flow, 0.15 mgd times 6,400 milligram per liter times 8.34 means we're wasting 8,006 pounds per day. You can probably do the math in your head because what we're going to do in step 3 is take the pounds under aeration, 40,000 divided by the pounds of solids that are leaving through the waste activated sludge flow, 40,000 divided by 8,000. What number is that? I think you can probably do it in your head. So go ahead and type out the number if you have one. We have any answers, Owen?
Yes, they're rolling in 5.
Very
days.
good. Very good. So 40,032 divided by 8,006 gives us about 5 days. So the solids are remaining for 5 days. And that seems like a good number for a conventional activated sludge facility. Now,
We did
I
have a
wanted
quick
to,
question come
yes,
in.
do it.
So they were just wondering for MLSS samples, what's typically used to be the representative of the plant? How many, number-wise? If it makes sense.
Yeah, could you read that again? I'm not sure.
Yeah, how many, sorry, the wording on my end was bad there. How many MLSS samples are typically used to be representative of the plant?
Oh, I see. Well, most of the systems that I've dealt with, the operator will take one good sample per day and go through this process. I believe that if you were having a problem though in the plant, or there's lots of variation throughout the day, it may be a situation where you would take more than one. I hope that answers the question. If that didn't answer the question well, but let me know in the chat. But they'll take a sample at the end of the aeration basin, and the aeration basin is mixing. So when you collect a 1 liter sample, you can use that for a lot of different things. You can look at how well it's settling. And you can also calculate the MLSS and the MLVSS from that sample. Now, 1 per day is what I've seen. And if anybody else, any lab people or experienced operators want to add to that answer and add your expertise, please do so. And Owen will let me know and we'll share it with everyone. That good, Owen, for now, and you'll watch out for that?
Yeah.
Okay. So now we have the same equation, but I've added a little bit to it here. In this form of the equation, we have basically 3 pounds formulas. In the top here, we're looking at the total amount of solids under aeration. And in this case, we're using the aeration tank volume and the operational volume of the clarifier. And we're using the same MLSS for both because it is the same solids concentration because the contents of the aeration basin just pours into the secondary clarifier. On the bottom, we have 2 different pounds formulas. We have on the left, we have the pounds per day of solids that are leaving in the waste activated sludge flow, which is the majority of solids that are leaving. But then we also add an additional pounds formula here to account for any solids that are leaving in the effluent. Be a small amount, but sometimes you might want to account for everything. And this might be a form of an equation that you would see also on a certification test. And I'll show you how that might work here. Here's an example. Here we're accounting for everything. In this one, we have the aeration tank volume and the clarifier volume. The aeration tank is 1 mg, and the operational volume of the secondary clarifier is 0.25 mg, 250,000. And the MLSS concentration is 2050. So if we put that into the top of that equation, you can see those numbers here. We just added the volumes and used the same MLSS. On the bottom left, we include the information for the waste activated sludge flow. 0.055 mgd times the concentration of the waste activated sludge, 7,980 milligrams per liter times 8.34. And then finally, we use the plant flow. The plant flow is 3.25 mgd, and the effluent suspended solids that are measured in the effluent, 21.2 milligrams per liter in this case, times 8.34. So we add those 2 on the bottom to get the total solids that are leaving, and we include the clarifier. And when we resolve those, we get 21,371 pounds under aeration and 4,235 pounds leaving, and it comes out to about 5.05 days. So that is an example of MCRT with all the information. And so let's go ahead and do poll 3 here, where I'm going to ask you to estimate the MCRT for a plant that has 30,000 pounds of MLSS under aeration and a wasting rate that eliminates 5,000 pounds per day of suspended solids.
Okay. Might do a little shorter on this poll just because we're getting a lot of responses and quickly give it
Good.
another 15, 20 seconds.
And you can just give me the top answer.
Absolutely. Okay, I think we're good to go. So I'll close that out and share it quickly. Top answer was 6 days at 91%.
Excellent job. And 30,000 pounds divided by 5,000 pounds is 6 days. And how we use this for process control, you see if you increase the wasting rate, you actually end up decreasing the MCRT. And if you decrease the wasting rate, you're holding more solids and you're increasing the MCRT. And the reason why we're doing this, why we're doing this FM ratio calculation and the MCRT calculation, there's a couple different goals. One goal is to have a good, healthy sludge. We want our microorganisms to be healthy enough to remove BOD. So we don't want to overly stress them or starve them or overfeed them. We want just the right amount of food to microorganisms and the right kind of sludge that settles well and forms flock well. Here's a example of FM ratio compared to the settling. And you notice for conventional sludge there, this line right there, it's representing that 0.25 to 0.45 FM ratio. And you notice that red line shows a lot better settling. You have a lot better sludge density and better settling when you hit that FM ratio. And there's some gaps between. So if you were above the FM ratio range or below, you could have some problems with settling. That's why I kind of answered the question earlier about settling the way I did. If you adjust, given that you don't have filamentous bacteria or some kind of toxicity, adjusting the FM ratio could be the solution to getting a better settled sludge. Also, if you have a high rate system where you have a lot of food and you know, you're not holding the solids for a super long time, you'll get simpler types of organisms like amoeboids and bacteria and free-swimming xylates. Right in the center of a conventional sludge, you'll get a lot of like stock xylates, but not the real complex organisms. You don't start seeing things like rotifers in large numbers until you have extended aeration. So you're holding the solids for long enough where more complex species will develop. And there's a couple things I would say about that. You can look through the microscope to see the health of your microorganisms, to get an idea of the overall age of the sludge. But also all these different types of organisms would settle differently. If you have extended aeration, rotifers they're going to settle differently than a bunch of bacteria. So it affects the way they settle. Now let's delve quickly into some lagoon ideas, and I wanted to share with you a typical lagoon treatment system. It's also secondary treatment, and it's usually designed so that your first cell is a reactor cell, a lot of aeration and removing most of the BOD. The second cell is where you want to have the conversion of ammonia to nitrate, and then the final cell is just settling and polishing. And retention time is a big deal because you want to maintain contact between the BOD, the bacteria, and DO as long as possible. So I'll give you an idea of how you would calculate the theoretical retention time of a lagoon. We have a lagoon that's 10 feet deep, 200 foot wide, 300 foot long. And so I calculate the volume by saying 10 foot times 200 foot times 300 foot, and then I'm going to use this conversion factor, 7.48 gallons per cubic foot. That converts it to gallons. That's a constant. So I get 4,488,000 gallons, and I can convert that to mg by either dividing by a million or moving the decimal 6 places to the left. So 4.488 mg, and I can calculate the retention time by dividing by the flow. The volume divided by the flow gives me the time. 4.488 mg divided by 0.2 mg per day, 22.4 days. But remember, this is just theoretical. We're assuming that we don't have sludge buildup and we don't have any short circuiting. Now I'm going to give you a chance in poll 4 to do a similar calculation, but assuming that the bottom 2 feet are filled up with sludge and assuming we don't have short circuiting. I'm running out of time today because I'm so slow. So we'll just give a minute for this one, and then I'm going to show you the organic and hydraulic loading for trickling filters. And it would probably be done within about 7 minutes, if that's okay. I'm going a little bit over. I hope that works for everyone. Go ahead and tell me the top answer.
Yeah, I'll do that. I'll just also let people know if you do end up having to leave, no worries. There will be a recording of this sent out in the follow-up email. You should still be receiving your certificate. Just so at the end we can go through the questions that are remaining as well. Let me close this out. And the top poll result was 18 days at 65%.
Excellent job. And because we no longer have 10 foot, we have 8 foot depth because the bottom 2 feet are sludged up. So that reduces our volume to 3.59 and divided by the 0.2 flow gives us about 18 days. Now there's some other things though that can affect the retention time, the actual retention time, and that's short circuiting. You see where they used some dye here and some flow modeling, and these blue areas in the cells, especially cell 2 and 3, indicate totally unused capacity. That's because water is taking a shortcut from the inlet to the outlet. So we're, instead of 20 plus days, we're only getting about maybe 3 or 4 days of treatment in those cells. Some things that you can do to evaluate short circuiting is to measure the dissolved oxygen level and temperature at multiple depths and locations in the lagoon. That'll let you know if you're getting good enough mixing. You can also put some floatable objects in the inlet and see what path they take and how quickly they move from the inlet to outlet. In this particular instance here, these floating fruits made it to the outlet in about 6 days, which is significantly less than 20 days. It was taking a shortcut down the berm. They moved the floating aerators a little bit to force that flow to take a different direction, and they increased the retention time by about double, so they doubled the treatment. You can also install floating baffles. These curtain baffles, they have a flotation device on top and an anchor at the bottom, and it forces the wastewater to take a serpentine path through the lagoon. And here's an example of some lagoons. You can see the baffles there, and it's forcing that to take a route that's serpentine, and you get better treatment. Let's move right on to trickling filters here. In this case, the microorganisms are not suspended. They're an attached growth as a biofilm to media, and the wastewater trickles over and through the trickling filter. The trickling filter has either synthetic media or rock, and the biofilm grows on this media, and it's sprayed and distributed throughout by a rotating spray device. There's a recirculation flow that brings water back from the clarifier, treated water back from the clarifier, that can be added to the influent to decrease the organic loading. So if you have a real high BOD, you can add recirculation water. It reduces it down to a level that biofilm can handle. And when you recirculate that, you're also adding to the hydraulic loading though. The organic loading is calculated as pounds of BOD per day for every 1,000 cubic foot. And we want that to range between about 5 and 25 pounds per day. The lower pounds per day are for systems that also want to treat ammonia and have nitrification occurring. And keep in mind that 1,000 cubic foot is part of the units that we want to end up with, and I'll show you how we do that. If the organic loading is too high, we could have excessive biofilm growth and even have septicity, and it could clog the trickling filter and cause some problems. The excessive biofilm growth would actually also reduce nitrification. If it's too low, you're not feeding your microorganisms enough, and they can become unhealthy. Here's an example of an organic loading calculation. We have a total flow that's going to this filter of 0.85 mgd, and the BOD concentration is 95 milligrams per liter. And we want to calculate the organic loading per day per 1,000 cubic foot. And the trickling filter is a large trickling filter, has a diameter of 100 feet and a media depth of 6 foot. And there's a little diagram of our trickling filter, not to scale, but 100 feet by 6. So first of all, we would, just like the other process control, we would calculate the pounds per day of BOD. 0.85 mgd is our flow. 95 milligrams per liter is our concentration of BOD times 8.34 pounds, means we're adding 673.5 pounds per day of BOD to this filter. And then we calculate the volume of the filter. And I'm using D squared times 0.785 instead of pi r squared. So diameter times 0.785 times the depth. So 100 feet times 100 feet times 0.785 times 6 foot gives us 47,100 cubic foot. That's our volume in cubic foot. Then we simply divide those two numbers. 673.5 pounds per day divided by 47,100. But notice what I did on the bottom there. I separated out the 47.1 from the 1,000 cubic feet because we want to retain that 1,000 cubic foot in our units so we can compare apples with apples. So you notice I took 673.5 divided by 47.1 to get 14.3 pounds per day per 1,000 cubic foot. Let me know if that makes sense to you, the way I did that at the bottom. And notice also this is between 5 and 25 pounds per day. So we're in the larger range. For the hydraulic loading rate, there's a range between 25 and 100 gallons per day per foot. If it's too low, you won't have enough water to clean the filter, so you could end up getting clogging and filter flies and septicity. If it's too high, think of like a pressure sprayer, you'd be washing off the media, the biofilm, unnecessarily, and you'll see increased sloughing in the effluent. So if it's too high, did my audio click off for a second there, Owen?
Yes, it did.
Oh, did we lose anything, or was it just 1 second?
It was a solid 5 seconds or so. We missed a chunk of that.
Oh, sorry about that, everyone. So here's where we were discussing the hydraulic loading rate, plant flow in gallons per day divided by the surface area of the filter in square feet. So we're going to try that. So we have a filter that has a diameter of 60 foot, and the flow is 0.15 mgd, and the recirculation rate is 0.13 mgd. So we're separating out the inflow from the primary clarifier and the recirculation. So we're going to have to add those together to get the total flow. And we're going to calculate the hydraulic loading rate on the filter in gallons per day per square foot. So what do we need to know? First, we'll calculate the total flow in mgd by adding that 0.15 mgd from the primary clarifier and then adding the recirculation flow of 0.13 mgd, and that gives us a total of 0.28 mgd of flow. We got to convert that to gallons per day, and we do that by just timesing it, the mgd times a million. 0.28 times a million gives us 280,000 gallons per day. Then we need to determine the surface area of the filter. Now for this, I'm using diameter squared times 0.785 to get the surface area. So the diameter is 60 foot. 60 foot times 60 foot times 0.785 gives me a total surface area of 2,826 feet. Now we have everything we need to complete this equation. Gallons per day divided by the area, and we get a hydraulic loading of 280,000 gallons per day divided by 2,826 square feet. And that gives us this figure of 99.07 gallons per day per cubic foot. Now it's technically within the range, but that looks like it's a pretty hot hydraulic loading rate, and we might actually be getting some unnecessary washing away of our media. So we'd have to watch that. It's definitely on the high side. And we'll do our last poll here. And the question is, the operator of a trickling filter plant in a resort community detects signs of excessive biofilm growth at the onset of the tourist season. And what would we do?
I'll let everyone know we're going to be pretty over in time. So the questions, I've collected the questions. I think what we'll do is I will send them over to Greg, and then in the follow-up email, we will send them out. So you will have your responses.
Okay, and if anyone wants to hang around, or if it's kosher to hang around a little bit, I will hang around as long as there's reason to. But if you think it's better to, whatever you think is best, Owen.
Okay. I'm thinking we'll probably send them over to you just because we have like 10 or 12 questions rolling in. So it's
Okay.
probably going to take quite a while. Yeah.
Well, thank you everyone for putting up with my slowness today.
Okay. So I'm going to close out this poll. Um, Results wise, 58% of people said increase the recirculation rate, and 25% said decrease the recirculation rate. 10% add additional BOD to stimulate the process. 7% said dose the influent stream with mild chlorine solution.
Okay. And most likely, this tourist town at the onset of the tourist season has experienced increased BOD. So the BOD is increased, and it's causing this excessive growth of biofilm. So that's a sign of a little bit of organic loading or overloading. So we can increase the recirculation rate, which adds treated water and kind of dilutes that BOD. So that would be one of the first things that you could do. And so that's what we covered today. We spanned a large portion of process control for secondary wastewater treatment processes. We looked at FM ratios, MCRTs, we looked at retention time for lagoons, and we looked at organic and hydraulic loading of trickling filters. This was a little bit of an experimental webinar I did because I tried to cover a large portion so that we could make like connections between secondary treatment processes that are common and look at how they manifest themselves in activated sludge, lagoons, and trickling filters. I hope you enjoyed it. If you have something that you enjoyed learning about today that you'd like to share in the chat, you're welcome. And Owen's going to take care of the questions and send them to me. And I will also share my email here, gpearson@mtu.edu. If you want to ask me anything directly, you're allowed to do that. And I'll do my best to provide information and answer your questions. And that's all for me. I'm going to be quiet now and let Owen take it over from here.
Okay, so a huge thank you to Greg for sharing his expertise with us today. Following this webinar, you will receive a follow-up email with the slides from today and a link to the recording. We also ask that you complete the webinar evaluation following the webinar so that you can let us know your thoughts on today's session, as it helps us plan for future webinars on topics that are important to you. So thank you again, and we hope to see you at future EFCN events.
Thank you, Owen. Thank you, everyone.